using the second derivative tests. Okay, so we're going to do what we said we were going to do up above. So we're going to find the stationary critical points. Okay, so we need to find our derivative. So we've got f prime of x. So look at this function. It's a product. We're going to have to use a product rule, right? So it's going to be the first function, 4 minus x, times the derivative of the second function. So the derivative of e to the x is just e to the x, plus the second function, that's e to the x, times the derivative of the first function. The derivative of 4 minus x is just -1. Okay, so here's our derivative. 4 minus x e to the x minus e to the x. And we've got an e to the x in both these terms here. I'm going to sort of factor that out because it's going to make it a little bit easier when we solve it anyways. Set it equal to 0 and solve. So if we factor out e to the x from this, we're going to be left with 4 minus x from here, and we factor e to the x out of minus e to the x, it's just going to be -1. I'm going to write that factor, that e to the x factor we just pulled out at the end of that. Okay, and look what happens. We get a really similar function, except it looks like this. Inside here, 4 minus x minus 1 is basically 3 minus x. And we still get e to the x. So our first derivative looks pretty similar to our original function. So we're going to set to 0. And we're going to solve. So let's see, we get 3 minus x, that quantity, times e to the x is equal to 0. Well, it's obvious that if 3 minus x is equal to 0, the derivative is going to be equal to 0. And how about this? E to the x is equal to 0. When is that going to be equal to 0? Never, right? No solutions from this part. So we only have one critical point. It's a stationary critical point. So we can use this now, right? Here's our stationary critical point. We can use this in the second derivative test. Okay, so the second part, right, we found the stationary points. The second part is evaluate the stationary point, the stationary critical point, in the second derivative. So we want to know, well, I guess first we had to find the second derivative, which we haven't done yet. So our first derivative is this, 3 minus x e to the x. And because our first derivative was so similar to our original function, our second derivative is going to be pretty similar too. So let's see what happens. We got to use the product rule again. So it's going to be 3 minus x, the first function, times the derivative of the second function. So e to the x is the second function, and the derivative of that is e to the x. And then it's going to be plus the second function, which is e to the x, times the derivative of the first function. The derivative of 3 minus x is just -1. So I'm going to do this pretty quick. I'm going to tidy things up like we did last time. So that's 3 minus x e to the x minus e to the x. And if you factor out that x again, that e to the x again, we're going to be left with 2 minus x e to the x. And I bet you can guess what the third derivative is, because there's a pattern sort of going on for this. But we've got that second derivative. We're going to evaluate the second derivative at the critical point. And so what do we get? The second derivative evaluated at our critical point is 3, right? So we're going to evaluate it at 3. It's going to be equal to 2 minus 3 times e raised to the 3. Well, 2 minus 3 is negative 1. Negative 1 times e to the 3 is just negative e to the 3. Now, what's the only thing we really care about this? All we care about is this going to be a positive value or a negative value. So in this case, right, it's negative. So the second derivative is less than 0, which means that at x equals 3, f of x is concave down. Okay, so the second derivative tells us it's concave down, and here's where I said, this is where I'm going to draw my picture. Here's our critical point at x equals 3. So here's 3, right? Here's our critical point. It's concave down at that value, so it's going to look like this. It should be obvious. This is going to be a relative max. So we get a relative max it occurs at x equals 3. And the relative max, remember, the maximum is the value of the function. So if we evaluate the original function at 3, that'll be the relative max. And so the original function is 4 minus x, so it's going to be 4 minus 3 times e raised to the x, and x is 3, so e to the 3. E to the 3 is the relative max, and it occurs at x equals 3. Alright, so let's take a look. I was smart enough this time to actually graph this, and I brought the graph down and stuck it here. Here's the graph of our function. Actually, I can pull it up. I still have it on my... Let's go to Smart View. Here's our function, right? 4 minus x times e raised to the x. Let's take a look at what that looks like. Just graph it and maybe make that even bigger. So there's our function. 1, 2, 3. There it is. That's our maximum. So e to the 3, it's someplace, so e is a little less than 3. So, I don't know, it's about 25, something like that, a little less than 27. Alright. Actually, I don't think it's quite that big, because I think I made my, this goes to 20, so that's probably, this goes to 25, I think, so this is probably about 20. Okay, so there's the second derivative test. So you've got a couple of ways to find your relative min and your relative max. One way is to use the first derivative test. And the nice thing about that is it works no matter what kind of critical point you have, whether it's a stationary point or whether it's a point of non-differentiability. But you know, there's a certain elegance to this second derivative test too, but it'll only work if you've got a stationary critical point. And you know, if it's pretty easy to find the second derivative, I'd probably use the second derivative test. You know, you avoid having to make the sign chart and analyze that to figure out if you get an increasing or decreasing. If it's sort of a pain to find the second derivative, I'd probably just stick with the first derivative test for that. Okay, so that's it.